Hello and good afternoon, ladies and gentlemen. Let me begin with the name of Allah, who is the most beneficent and most merciful. My name is Muhammad Adil Munir, and I am Session Manager of Session 18, Water Track 3. I am working as a lecturer in the Department of Mechanical Engineering, University of Engineering and Technology, Lahore, New Campus. On the behalf of Complete Organizing Committee, I warmly welcome you all to Session 18, Water Track 3 of International Conference of Energy, Water and Environment, ICEWE 2021.
Our session chair is Dr. Sanja Armakovic. In this session, there are total of 5 talks. At the end of each talk, we will be having question and answer session. The audience is requested to write the questions in the chat box during the talk. At the end of each presentation, the session manager will ask the requested questions from the presenter. Without any further delay, let me introduce our session chair, Dr. Sanja Armakovic. She is working as an assistant professor in Faculty of Sciences, University of Novi Sad, Republic of Serbia. She is co-founder and vice president of EDASCO, and she is editorial board member of 2 journals. One is Advanced Journal of Chemistry, Section B, Natural Products and Medical Chemistry, and second is Advanced Journal of Science and Engineering. She is also member of Tandorio Aikido Club Sionkan. The topic of her presentation is application of titanium oxide nanomaterial for water purification based on photocatalyst. It's honor to have you with us, Dr. Sanja. I humbly request you to please share your thoughts.
Dear colleagues, my name is Sanja Armakovic, and I'm working as an assistant professor at the Faculty of Sciences, University of Novi Sad from the Republic of Serbia. I'm also co-founder and board member of the Association for the International Development of Academic and Scientific Collaboration. It is my pleasure to present results about the application of titanium dioxide nanomaterials for water purification based on photocatalysis. The problem of environmental pollution is very serious, and increasing attention is dedicated to toxic pharmaceutics. The high thermal stability of these substances leads to the accumulation in the environment. When speaking of pollutants in the environment, one usually thinks of chemicals that are used to treat plants and soil. Active components of pharmaceuticals have slowly, one might say by the back door, entered the environment with the primary purpose of helping people. Pharmaceuticals have been detected in ground, surface, drinking water, and ocean water sediment in soil. An effective way to deal with this problem is the degradation of the drug by advanced oxidation processes, based on the formation of hydroxy and other radicals. Many advantages of titanium dioxide over the broad range of other nanomaterials have led to the situation where titanium dioxide is one of the most frequently employed photocatalytic materials. Many organic substances and their intermediates are in this way completely mineralized. Metoprolol is a selective beta blocker that is used to treat a variety of cardiovascular diseases. Metoprolol shows slow direct phototransformation and hydrolysis. Because of this fact, metoprolol is a good example for our study. It was detected in all kinds of environmental water, and also in drinking water in some countries. For the purpose of photocatalytic degradation of hazardous pollutants in water, titanium dioxide has been recognized as the most preferable material due to the high photosensitivity, non-toxic nature, and stability. For this study, we use two commercial catalysts, Degussa P25 and Wacker. Degussa is combination of anatase and rutyl forms, while Wacker is pure anatase. In this regard, oxide nanomaterials have exhibited great potential for practical applications in a wide range of areas, because of which it is important to understand their photocatalytic properties under several conditions. The aim of this work was to make a detailed comparison of the kinetics of photodegradation of metoprolol, synthesized by Wacker and Degussa in an aqueous solution under a variety of experimental conditions. The effect of the temperature and pH, initial pH value were studied. The initial metoprolol concentration was 0.05 milliem, and the catalyst loading was 1 milligram per milliliter. For the kinetic study for metoprolol, we used liquid chromatography with a DAD detector, and aliquots of half milliliters were taken from the reaction mixture at the beginning of the experiment and at the regular time intervals. The suspensions were filtered through millipore membranes. And what we got? The specific surface plays a significant role when it comes to the photocatalytic properties of nanostructured and porous titanium dioxide. The photocatalytic activity of Wacker was compared with the most commonly used form of titanium dioxide, Degussa, under the influence of UV radiation. The efficiency of photocatalytic degradation differs depends on the catalyst use at the same temperature and pH. Faster decomposition of metoprolol was established when the Wacker form was used, of course comparing with the Degussa. Higher temperature than 298 Kelvin or 25 Celsius degree contribute to increased degradation efficiency in both cases. After only 30 minutes, metoprolol was completely removed from solution. The Wacker form has much larger particles than the Degussa, which results in 6 times smaller specific surface area. However, the higher degree of radiation scattering in the Degussa catalyst compared to the Wacker is why the Degussa is a less efficient catalyst at each temperature and also pH value of the solution. The pH of the solution has a significant influence of the electrostatic interaction between catalyst surface and metoprolol. Therefore, we investigated the influence of the initial pH of the degradation in water suspension in the interval from 3 to 11. Significant differences in the degradation rate of metoprolol at different pH have been observed. Obtained results of metoprolol degradation with the changes of pH can be explained through consideration of surface charge of catalyst and pK of metoprolol. pK for metoprolol is 9.7. When the pH is lower than the isoelectric point of the catalyst, then the surface is positively charged, and the cations are being attracted while the anions are repelled. Met contains amino group. When pH is less than pK, condition is fulfilled for its protonation. Taking into account that the isoelectric point of catalyst is around 6 and the pK of metoprolol is 9.7. Within the interval at 6 to 9.7, electrostatic attraction is favored between negatively charged catalyst surface and protonated metoprolol, which explains higher degradation efficiency at mentioned pH 7 and 9. The speed of degradation is different for each catalyst. And what happened for the pH value of 9 in case of Wacker still remains to be explained. On the other side, for pH less than 6, both catalyst and substrate are positively charged, which increase electrostatic diffusion and decreases the degradation efficiency. However, in pH higher than pK of metoprolol, the loss of proton from the hydroxy group at a pH of 11 leads to the decrease of degradation efficiency, since both compound and catalyst are negatively charged. What we can conclude and what we actually did, the study of photocatalytic degradation of metoprolol in the presence of commercially available forms of titanium dioxide has been performed. The study aims to evaluate this material's efficiency for moving metoprolol from water through analysis of the kinetics of photocatalytic degradation. This study also accompanies the investigation of the influence of temperature. It has been found that the Wacker form of titanium dioxide performs better when it comes to the photocatalytic removal of metoprolol from water. In cases of both photocatalysts, the higher temperature contributed to the faster degradation of metoprolol. The initial pH of the solution has proven to be very important to photocatalytic degradation of metoprolol. The most efficient degradation was achieved at 7 and 9, when the substance positively and catalyst negatively charged. In the end, I would like to acknowledge the support received by Ministry of the Education, Science and Technological Development of the Republic of Serbia. Also, I would like to thank my friends and colleagues from the EDASCO for their efforts to participate in this great event constructively. Feel free to visit our website. Also, once again, many thanks to the organizers of this outstanding event. In case you have some questions, comments, or suggestions, for example, for our results with Wacker at pH 9, feel free to contact me. Wishing you all the best.
Thank you very much, Dr. Sanja. If the audience have any question, you can ask in the chat box.
Thank you very much, Dr. Sanja, for your participation. I have one question from audience.
Yes.
Is the use of titanium oxide is sustainable environmentally and for the society?
Yes, it is very stable, and it is a very actually you can find titanium dioxide in the lot of actually other products, and it is stable in water a lot actually. But it is easy if you use titanium dioxide as a catalyst. It is very easy to remove it from the water, because if you have filters for actually for it, it is very easy and very useful to remove it from water.
Okay, thank you very much, Ms. Sanja.
Okay, thank you very much, Dr. Sanja, for being with us. Now, quickly moving forward, we have Mohammad Tahseen from USPCASW, Mehran University of Engineering and Technology, Jamshoro, joining us. The title of his presentation is Aerobic Biodegradation Monoethanolamine using Bacterial Consortium. I would humbly request Mohammad Tahseen to please share your thoughts.
Hello everyone, this is Mohammad Tahseen from US Pakistan Center for Advanced Studies in Government, Mehran University of Engineering Technology, Jamshedpur, Pakistan. I am going to present my conference paper on aerobic biodegradation of monoethylamine using bacterial consortium. First of all, the background. Monoethylamine is basically an amine-based compound mostly used for the capture of carbon dioxide. The wastewater was generated due to equipment losses, corrosion, volatile degradation, and reboiler tendency. The release of untreated or poorly treated wastewater into the environment can harm the local ecosystem as well as public health. So in this research, the biological treatment is used as it is economical environmental sustainable. Now coming to the methodology, first of all, I prepare the synthetic wastewater using the stock solution of bacterial medium, which are shown here to support the bacterial growth. And the concentration of monoethylamine was 10 gram per liter, while the municipal sludge was used for bacterial soils, which had a total solid of 3.5% and volatile solid 72%. And the pH of the synthetic wastewater was maintained at 7.5 using the stock solution of hydrochloric acid and sodium hydroxide. After that, I have transferred this wastewater to the phase reactor, in which the air was continuously was supplied using the aeration pump, and the COD ammonium nitrate of the reactor was monitored by using standard method AFA. After 9 days, the half of the volume of this reactor was discarded and the new volume was filled up with new synthetic wastewater, and the next cycle was started. And now coming toward the result, in the third cycle, I have achieved the maximum removal of monoethylamine. In this graph, you can easily say that COD was so rapidly removed in starting 5 days. In response of the COD removal, the ammonia was generated. After 5 days, the nitrification of process was started, in which the ammonia was also oxidized into nitrate, and after 9 days, the maximum removal of COD was achieved 95%, while ammonia and nitrate removal was 56% and 39% respectively. And the dry cell weight and optical density of this reactor was also monitored, which was shown in the figure. And the pH was also maintained at 7.5. As the COD was removed in the starting days, the pH was very high, because the intermediate product of monoethylamine was most maybe acetic acid and acetate, which are acidic compound, which change the pH, and so that the pH of this reactor was maintained at 7.5, because the optimum pH for the bacterial growth was 7.5. In the conclusion, monoethylamine was biodegraded by bacterial consortium into the carbon dioxide and ammonia, while the nitrate bacteria also oxidized the ammonia into the nitrate, which was consumed by bacteria as a nitrogen source. In this research, the COD was efficiently biodegraded by bacterial consortium, and maximum COD removal was achieved 95%, while the ammonia and nitrate was also removed, which was very low. That's it. Thank you.
Ladies and gentlemen, this was Mohammad Tahseen. Thank you very much, sir. If the audience have any question, you can ask in the chat box.
Okay, thank you very much, Mr. Mohammad Tahseen, for joining us. I have one question from the audience. Can we use this method to capture carbon dioxide for mobile sources which are not on fixed location, for example, vehicles? And if yes, then is it economical for them or not?
Sorry, sir, I cannot understand your question.
Okay, I repeat my question. Can we use this method, your proposed method, to capture carbon dioxide for mobile sources like vehicles? And is it economically feasible or not?
Sir, basically, I am degrade this monoethylamine. Basically, this amine solution was used for the capturing of carbon dioxide for industrial purposes. For vehicle purposes, it is not feasible.
Okay, thank you very much.
Okay, thank you, sir. Now I am moving towards the next speaker. His name is Jawad Ahmed and he is from Prime Chemicals, Karachi. His title is Reclamation of Cooling Tower Blow Down Water Using Recycled End of Life RO Membrane. I would humbly request Mr. Muhammad Jawad to please share your thoughts.
Bismillahirrahmanirrahim. Assalamu alaikum and hello everyone. My name is Jawad Ahmed and I'm from Prime Chemicals Corporation. The title of my presentation today is Reclamation of Cooling Tower Blowdown Water Using Recycled End-of-Life RO Membranes. So here's a brief introduction of the background of what this project is all about. Reverse osmosis accounts for around 2/3 of the worldwide desalination capacity, which means that at any given day, around 65 million meter cube of desalinated water is being produced through brackish and seawater reverse osmosis desalination plants worldwide. And after use in these desalination plants, around a little shy of 1 million RO membranes are being discarded worldwide, which represents a solid waste generation of over 14,000 tons per annum worldwide. So different options have been considered in the last decade or so to use or recycle these discarded end-of-life RO membranes for useful applications. And one of the most attractive propositions that has been considered is to use these discarded RO membranes as ultrafiltration membranes after removing the active polyimide layer through oxidation and exposing the underlying polysulfone layer, which is automatically in the ultrafiltration range. So a whole new lot of possibilities spring up for these for the application of these recycled membranes, which are basically everything in the ultrafiltration spectrum. And some of the case studies, that are relevant to this aspect is the recycling of tertiary wastewater, recycling of grey water, which we have published last year, a case study on grey water recycling. And now for this, the current presentation, we are considering cooling tower blow down water recycling through discarded RO membranes. So the materials and methods that we have used here is the membrane that we have used. It's a Lanxess Leverbrain 4-inch 4-inch diameter, 40-inch long RO membrane with membrane permeability of 2.5 LMH per bar and a virgin membrane salt rejection of 99.5%. The membrane was discarded after 12 months of operation. And after the membrane was discarded, it was subjected to membrane cleaning in cycles of alkaline and acidic cleaning. And this was followed by a membrane conversion process by exposing the membrane to sodium hypochlorite exposure of 300,000 ppm hours. So these, the detail of these materials and methods has been published, and obviously the results of the conversion process have been published by our team last year. And in consideration of the cooling tower blowdown feed water that we have used for this study, here are the cooling tower blowdown feed water parameters, and these are compared with the cooling tower blowdown feed water from previous literature, published literature. So here's the skid, the CAD diagram of the skid that we use. And on the left and on the right, here's the picture, the snapshot of the filtration skid in application. And on the right, you can see the cooling tower where we are taking the feed for this filtration experiment. So proceeding towards the results, these are summarized over here in the form of membrane permeability. We can see that before the conversion process, the membrane permeability was 2.5 LMH per bar, and after the removal of the polyamide layer, the membrane permeability increased over 10 folds to 35.4 LMH per bar. And the salt rejection, which was higher than 90%, it was reduced to less than 5%. Confirming the membrane conversion to ultrafiltration from reverse osmosis. And here's the for the feed water, the cooling tower feed water, the feed water particle size for the feed water on the left, and the screenshot of the particle size analyzer on the right. And we can see over here that the transmittance is 100%, which means that no particle above the minimum detection limit of the analyzer was present in the filtrate, which was 0.1 microns. So we can conclude that all particles above 0.1 microns were rejected by this membrane, confirming its operation as an ultrafiltration membrane. And here's a statistical summary of the rejection parameters. We can see a median particle size of around 276 micrometers in the feed water, and less than 0.1 micrometers in the filtrate water, confirming again its conversion into an ultrafiltration membrane. So the results in the form of turbidity, we can see the feed water turbidity on the left. For the current scenario, it varied from less than 10 NTU to over 100 NTU, with a mean value around 40 NTU. And in the filtrate, we had a median value of around 1.6 or 1.7 NTU, and we can see a drastic reduction with all data sets lying below 3.5 NTU and primarily below 2 NTU. So from here we can see the average removal of over 95% in terms of turbidity. So another parameter that we analyzed was the silt density index, or it's again a measure of the particles that are present in the water and their propensity to cause fouling on the RO membrane, the downstream RO membrane. And on the left, we can see the feed water with an SDI of over 5, and we can see the visible presence of colloids and particulates on this SDI filter paper in the feed water. And for the filtrate, we can see that there's almost no deposition with an SDI value of less than 1. And we also calculated the modified fouling index, or the MFI value, and which represents the slope of the curve over here. The slope of the curve in the central region, which can be shown through the point pointer over here, and the slope was calculated to be 0.109. With a regression coefficient of 99.95, and again less than 1 is generally recommended for feed to RO membrane. So our value is 0.1 against a recommended value of less than 1. So it's excellent feed water for the downstream RO membranes. Again, it represents excellent conditioning of the membrane of the water for feed to RO membrane. So to summarize the conclusions, we found sustained operation with filtrate turbidities of less than 2 NTU for a wide range of feed turbidities. And we found SDI of the filtrate to be less than 1, the MFI value of the filtrate also to be less than 1, which again represents excellent conditioning of the water for downstream feed to RO membranes. And obviously the particle size was less than 0.1 micrometers. Recommendations for future work is to extend the pilot application for other similar challenging feed streams, including tertiary wastewater. We've covered grey water in one of the past published publications, and there are some of the other potential ideas that this idea can be applied to. And obviously, one of the most important aspects that needs to be covered is full-scale testing for long-term applications. This is one of the major data gaps that currently exists. So I'd like to thank my company, Prime Chemicals Corporation. This work was part of a research and development R&D collaboration between Prime Chemicals Corporation and National University of Sciences and Technology through a memorandum of understanding on research on membranes for water and wastewater treatment. We have also received support from Pakistan Desalination Association. So we are working in collaboration with the academia and industry, and we are open to more collaborations with other institutes that are working in the field of water to enhance or to form a major alliance to solve the industry problems and obviously to contribute towards the academia as well. So the differences are flashed over here. I'd like to thank you all for listening or being audience to this presentation, and thank you for your audience. Thank you.
Okay, thank you, Mr. Jawad Ahmad. From the audience, if you have any question, you can ask in the chat box.
Thank you very much, Mr. Mohammad Jawad, for joining us. I have one question from the audience. As we know that there are three dimensions of sustainability. One is economic, second is environment, and third one is society. So is your proposed method is economically sustainable? Have you done any cost benefit analysis?
Yes, can you hear me?
Sorry,
Am
Mr.
I
Mohammad
audible?
Jawad.
Am I audible?
Okay, Mr. Mohammad Jawad, my question was that have you done any cost benefit analysis for your proposed method?
Am I audible, sir?
Yes, you are audible.
Hello?
Yes, Mr. Jawad, you are audible. Please proceed. Have you got my question? Okay, I think there is some network issue on the side of Mr. Mohammad Jawad. So thank you very much, Mr. Jawad, for joining us.
Okay, thank you, sir, for being with us. Now I am quickly moving towards the next speaker. Her name is Miss Asma Amir. She is from Pias, Islamabad, and her title is Synthesis and Characterization of High Surface Alumina for the Efficient Removal of Heavy Metal Ions. So I will humbly request with Miss Asma Amir, please share your thoughts.
Bismillahirrahmanirrahim. Assalamu alaikum. I am Asma Amir from Pakistan Institute of Engineering and Applied Sciences. And today I am presenting on the characterization of high surface alumina for the efficient removal of heavy metal ions. We all know that heavy metals are a constant threat for human health, and a lot of research is being carried on for the removal of heavy metal ions from water. The reason for choosing lead removal was that it affects nervous system, kidneys, and reproductive system. Especially, it causes mental retardation in children. Okay, next was the selection of the water purification technique. The reason to opt adsorption technique among water purification is that adsorption is very easy to operate and it is cost effective, and sometimes regeneration is also possible, and above all it is environment friendly as no toxic sludge is produced in this process. The reason to opt alumina as an adsorbent are its various useful properties. For example, its chemical inertness, regeneration properties, and its above all its surface physiochemical properties, which help in adsorption process. Next is the preparation and characterization of alumina powders. In this process, first of all, aqueous solution of urea and aqueous solution of aluminum nitrate were mixed by stirring. Then this mixture was transferred into an autoclave and heated for 24 hours at 120 degrees C. Then the wash and after 24 hours it was taken out and washing was done by filtration. Next was the drying of this whole thing, and it was dried in an oven for 24 hours at 85 degrees C. After drying, we got powder, which was AACH, ammonium aluminum carbonate hydroxide, which is the precursor for alumina. Next was the calcination of this AACH powder, and in my process, in my study, AACH was calcined at 3 different temperatures, that is 700 degrees C, 900 degrees C, and 1100 degrees C to get the alumina powder. The characterization techniques used in this study are X-ray diffraction, XRD, FTIR, Fourier transform infrared spectroscopy, scanning electron microscopy, and AAS, atomic absorption spectroscopy. Next was the methodology for adsorption experiment. In adsorption experiment, first of all, lead ion solution was prepared, and then lead ion solution was mixed with alumina. Like alumina was 0.01 gram of alumina, very minute quantity of alumina. Then this mixture was sonicated for some time. Then it was shaken in an orbital shaker for about an hour, followed by centrifuge, and after centrifuge, atomic absorption spectroscopy was performed to find the remaining concentration of lead after the adsorption experiment. Next are the results. This XRD graph is showing that after drying, we got AACH, ammonium aluminum carbonate hydroxide, and the XRD peaks are confirming that it is AACH. And when this AACH was calcined at different temperatures, then we at a lower temperature only gamma alumina was produced, but at higher temperature crystalline phases were produced like alpha and theta alumina. In the next is the FTIR curve, and in FTIR we can see that 468 aluminum oxygen vibrational peaks are observed, and for higher temperature calcined alumina, aluminum oxygen peak occurs at 544 per centimeter wave number. These are the scanning electron microscope micrographs, and these SEM images are showing the whisker-like morphology. And the advantage of whiskers-like morphology is that it has greater aspect ratio and higher surface area, which help in the adsorption process. Next are the effect of calcination temperature on removal efficiency. We can see that removal efficiency was highest in case of AACH calcined at lower temperature, 700 degrees C. The possible reason is that at higher temperature agglomeration takes place, and in agglomeration whiskers are agglomerated and intraporosity decreases, and this might be the reason for the lower removal efficiency at higher temperatures. Next graph is the effect of shaking time on removal efficiency. As the shaking time is increased, then more and more contact occurs between alumina and lead ions, and with increase of shaking time, all the sites are being occupied with lead ions. But after about 60 minutes, when all the sites of alumina are filled with lead ions, no further increase in removal efficiency occurs. This is basically the equilibrium time for this study. Next is the kinetic study. In kinetic study was studied through pseudo first order and pseudo second order model, and we can see that it was well fitted by pseudo second order model, and the correlation factor was about 0.988. And what it tells us, that it tells about the chemisorption of lead ions, means there occurs a chemical bond between lead ions and alumina, and when there is a chemical bonding between lead ions and alumina, it means that regeneration becomes very difficult in that case. Next are the adsorption equilibrium isotherms. Okay. Basically, the adsorption isotherms tells about the mode of adsorption, like monolayer or multi-layer formation, and the homogeneity of sites, and it was well fitted by Langmuir linear fit. And what does it mean? That Langmuir linear fit means that monolayer formation of lead ions on alumina will occur. And it also tells about the homogeneity of sites, means all the sites of alumina are equally accessible for lead ions. In conclusion, we can say that XRD confirmed the formation of AACH. Sample calcined at 700 degrees C and 900 degrees C had gamma phases, while while sample calcined at 1100 degrees C had theta and alumina phases in it. FTIR pattern showed the presence of aluminum oxygen bond, confirming the presence of alumina. SEM showed the whisker-like morphology for both AACH and alumina. By the increase of calcination temperature, removal efficiency was decreased, and it was highest for alumina calcined at 700 degrees C. By the increase of contact time, removal efficiency was increased. The equilibrium time was 60 minutes, after which there was no significant increase in removal efficiency. Kinetic data was best fitted with pseudo second order model, which favored the chemisorption of lead ions on alumina. Langmuir adsorption isotherm was coherent with the adsorption data, exhibiting the monolayer formation and homogeneity of adsorbent sites. These are some of the references from which I have taken help for this study. Thank you so much.
Thank you very much, Ms. Asma Amir, for your presentation. From the audience, if you want to ask any question, please paste your question in the chat box.
Okay, thank you very much, Ms. Asma Amir, for joining us. I have one question from the audience. As you have mentioned that you will use the alumina, so are there any harmful side effects for using the alumina?
Hello, am I audible to you?
Yes, you are audible to us. Have you got my question?
Yes, I have got your question. As I have mentioned that it is environment friendly and there is no toxic sludge produced in this method, so I don't think so that that it will cause any danger or any side effect.
Okay, thank you very much, Ms. Asma Amir.
Okay, thank you, Ms. Asma. Now I am moving towards the speaker 5. Next speaker, her name is Nadia Riaz, and she is from BZU Multan. And the title for her presentation is Investigation of Metal Organic Frameworks Based Water Desalination and Cooling System. I would like to humbly request Ms. Nadia Riaz to please share your thoughts.
Hi, this is Nadia Riaz from Bahauddin Zakaria University, Multan, and my co-authors are Hafiz Muhammad Asfahan, Dr. Muhammad Sultan, and our study topic is Investigation of Metal Organic Frameworks-Based Water Desalination and Cooling Systems. So, desalination is the process of converting the ocean's salty water to fresh drinkable water. But why desalination is so important to humans? Because of escalating water scarcity, contamination, and ever-increasing population density, which has hampered the local furnishers to attain demands for water quantities. And if you combine all the fresh water in the world from rivers, lakes, and streams, all of these will account for less than 1% of the total water on Earth, and even this 1% is not equally distributed. So the reasons such as Gulf suffers an extreme freshwater scarcity, but fortunately we have unlimited access to seawater which can desalinate and have fresh water. Therefore, researchers are conducting investigations to obtain membranes of high separation and use efficiency. As shown in the figure, the global water demand is expected to grow by 55% in 2050. The commonly employed desalination technologies are humidification-dehumidification, multi-effect distillation, solar distillation, multi-stage flash distillation, vapor compression distillation, nanofiltration, electrodialysis, reverse osmosis, forward osmosis, and adsorption desalination. Fundamentals of adsorption desalination are based on the adsorption and desorption phenomena. The whole system comprises of three major components. The first one is saline water evaporator, which is usually at a temperature of less than 25 degrees. Then we have a pair of adsorption bed or reactors, and then the third one, the last one, is condenser to consolidate the water vapors. The working of adsorption desalination system has been presented in the figure with all the components shown. In the first process, the surface area of adsorbent in the adsorption bed adsorbs by the vapor generated in evaporator. Heat of adsorption is released during this adsorption process. A cooling fluid is used to remove the heat generated in the bed to facilitate a continuous adsorption process. In the evaporator, chilled refrigerant is circulated through tubes, while seawater is sprayed over external surfaces of tube bundles as shown in the figure. Initially, the evaporation is occurred by a heat source that ranges from 2 to 25 degrees Celsius, but during the adsorption process, the evaporator pressure drops due to adsorption and contributes in the evaporation. The adsorption process ends when the adsorber bed reaches an equilibrium state. In the second process, low-grade waste energy or solar energy is used to generate the adsorbent. The desorbed vapor is circulated to a condenser to condense and stored as pure water in a collection tank. Cooling power during the adsorption period and potable water during the desorption period are the two beneficial outputs produced by the adsorption cooling and desalination system. So this was the working of conventional adsorption desalination system. So, discussing the pros and cons of desalination, its advantages include the ability to utilize waste heat, reduced operation and maintenance cost with reduced electricity consumption. Also, it has cogeneration ability, which is cooling effect and producing fresh water at the same time. Disadvantages of desalination include low cooling capacity and coefficient of performance. Operating parameters are very sensitive to performance indicators. A significant improvement in daily water production is reported in literature due to incorporation of suitable operating conditions. In case of adsorption desalination system, about 70% increment in daily water production has been recorded, whereas in case of dew point evaporative desalination system, about 89% of improvement in daily water production has been reported. The table shows typical operating parameters and their optimized values. First parameter is hot water inlet temperature for desorption or regeneration. Then we have cold water inlet temperature, chilled water inlet temperature, switching time, half cycle time, flow rate in desorption bed, flow rate in adsorption bed, flow rate in condenser, and their subsequent temperatures are also mentioned. The integration of organic compounds and transition metal ions have the potential to prevent the limited amount of functional building units plus operating difficulties that arise in the zeolite method, prompting researchers to develop realistic and strong adsorbing substances such as MOFs. Metal organic frameworks possess special properties which have high surface area, pore volume, low density, abundant adsorption sites, and various structure promoting different specific applications. The MOFs under consideration of the study are aluminum fumarate, MiL-101 chromium, and CpO27 nickel, and their structures are also shown in the figure. Then comes the results of the study that we have carried out. The figure shows the effect of hot fluid inlet temperature on specific daily water production of MOF materials compared to silica gel. At high regeneration temperatures, higher than 110 degrees Celsius, the CpO27 nickel was found to outperform the aluminum fumarate and silica gel, producing 4.3 cubic meter per ton in a day, which makes it suitable in applications operated with high temperature waste heat sources. On the other hand, the silica gel and aluminum fumarate were found to outperform CpO27 nickel at regeneration temperatures as low as 70 degrees Celsius, making them suitable in application utilizing low temperature waste heat or renewable energy resources such as solar energy. The figure shows the effect of the hot fluid inlet temperatures on specific cooling power of two systems compared to a silica gel system. The figure shows that increasing the hot fluid temperature will increase the SCP produced from two systems. The CpO27 nickel systems produced a cooling effect of 35.3 refrigeration tons per ton, while the aluminum fumarate system produced 22 tons of refrigeration per ton. Hence, it can be concluded that the cooling effect temperature is suitable for air conditioning applications. The figure shows the effect of hot fluid inlet temperature on specific daily water production of the two systems compared to silica gel system. The specific daily water production increased with increasing the hot fluid temperature at a hot fluid temperature of around 150 degrees Celsius. The aluminum fumarate system produced 6.3 cubic meter per ton in a day, while the CpO27 nickel desalination system produced 4.6 cubic meter per ton in a day. The silica gel system was found to produce 5.3 cubic meter per ton in a day at a hot fluid temperature of 90 degrees. It has been observed and can be concluded that metal organic framework materials such as aluminum fumarate, MiL-101 chromium, and CpO27 nickel showed great potential for adsorption desalination. Furthermore, the studied MOF materials are suitable for employment in thermally driven adsorption desalination systems. Also, the potential of MOF adsorbents is not completely realized as compared to typical porous adsorbent materials such as silica gel and zeolite. Hence, study highlights that there is great potential available to improve the performance efficiency by the employment of MOF adsorbents. Thank you very much for listening. All the questions are welcomed.
Okay, thank you very much, Ms. Nadia Riaz, for your presentation. From audience, if you have any question, you can paste your question in the chat box. Okay, thank you very much, Ms. Nadia Riaz, for your participation. I have one question from the audience. It is, as for the filtration is concerned, that TD's value for many other methods is less than 300, then why would we would prefer AD system? Can you listen my voice, Ms. Nadia Riaz?
Yes, sir. So
Okay,
can you
have you
please
got my
repeat the
question?
question? I wasn't able to hear your question. Can you please repeat your question?
Okay, okay, I am repeating my question. As for the filtration is concerned, the TD value for many other methods is less than 300. Then why would we would prefer AD system?
So there are many reasons. Most importantly, the MOFs that we are using in the case of ADS systems, they are more efficient while with ADS systems. In other processes, they are not as much efficient. Like for the case of ADS systems, the MOFs that we have applied and used are more beneficial, and they have shown better results.
Okay, thank you very much, Ms. Nadia Riaz. Okay, thank you very much, Ms. Nadia.
On the behalf of Organizing Committee of ICEWE 2021, I am very much thankful to the session chair, Dr. Sanja Armakovic, all the presenters and the participants. It was a wonderful session, and I hope the audience had enjoyed it. Hope to see you all in the next session as well. We have other sessions running in parallel and also the industrial exhibition. So enjoy our parallel sessions. Thank you again for sparing time for this productive session.